All right, welcome back. We are to the application part of what we've learned so far, and we are to optimization problems. And this is basically we're given some sort of a constraint, some sort of limiting factor. And based on that limiting factor, how can we maximize or minimize something? That, of course, in calculus terms means set up an equation, take the derivative and set it equal to zero. So that's going to be sort of the plan for these four problems that we're going to be going through. And I'm going to take time with this. The setup is the hardest part, in my opinion. And so I'm going to go ahead and read the problem. Problem one, a farmer wants to construct a rectangular pig pen using 100 feet of fencing. So that's our constraint, meaning that's all the fencing that we're going to be allowed to have. The pen will be built next to an existing stone wall. So only 3 sides of the fencing need to be constructed to enclose the pen. What dimensions should the farmer use to construct the pen of the largest possible area? So here's what we're trying to optimize in this case. This is our goal, is we want the largest possible area. So we're going to set up an equation for a rectangle, area of a rectangle. And I'm going to start by drawing a picture. And this will be the wall. So it says an existing stone wall. So this is the wall. And then we're going to have the actual pig pen itself. And there's only going to be 3 sides. And I'm going to label this side X, which makes this side also X. And I'm going to call this side Y. But we know the total needs to be 100. So if I the remaining fence is going to be Y. So if I subtract off 2 of the X's, this is actually going to be 100 minus 2X. Which means the area of the rectangle is going to be X times Y. But we're now going to rewrite Y in terms of X. Those of you going on to 3rd semester calculus, there's actually a more efficient way of doing this that you'll learn, but you need a lot more calculus to, to be able to do that. All right, I'm going to go ahead and distribute here. This is 100x minus 2x squared. And what we're going to need to do is to take the derivative so that we can optimize it. dA over dx is going to be 100 minus 4x. And to optimize this, meaning we want to have the minimum or the maximum, like we've talked about in the previous sections, that means we need to set the whole piece equal to 0. And solving for x, I'm going to get that x equals 25. And that'll be 25 feet in our case. So there's one of the dimensions that's here. To get y, I'm going to have to go 100 minus 2 times 25. So this is going to be a 25 foot by 50 foot pig pen. And that will give us the largest area. So again, we were given a constraint, only 100 feet of fencing, but how can we maximize the area? Well, here's the process. Come up with an equation, take the derivative, and then solve for the dimensions. We can even figure out what the area would be if I do 25 times 50. So this is the area max, would be 25 times 50, which is going to be 1,250 square feet. Now, it didn't ask for this information, but now we know. All right, problem 2. A rancher wants to construct 2 identical rectangular corrals using 300 feet of fencing. The rancher decides to build them adjacent to each other, so they share fencing on one side. What dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? All right, so again, the best way to do these problems is for you to pause the video and just read the problem over and over and over again, really get a good idea of what it is that's going on here. And so I'm going to come up with and the way they had it set up was they want two identical while sharing a side. And what I'm going to do is I'm going to let X, in this case, be one of these sides here, X, which makes that X, because they're all going to be the same. That's X and that's X. And I'm going to call each of these Y. Now, you don't have to set it up this way. There are many ways that you could set this up. This way just works best in my mind. And I'm going to notice that it says that there's a total of 300 feet of fencing. So let's add everything up for the fencing. And that's going to be X plus X plus X plus X. So that's going to be 4X plus 3Y needs to equal 300 feet. And what I'm going to do is I'm going to solve for Y. Now that might look kind of awkward, and that's certainly understandable. And please note that what we are looking for, once again, is the largest possible area. Now the area is going to be length times width, which means our area is going to be 2X times Y, just Y. We're going to assume that the fencing doesn't take up any area. That's not very realistic. Of course, fencing does, but we're going to simplify it by doing this. And of course, our area is 2x times y, which in this case is 300 minus 4x over 3. And I'm going to try to simplify this up a little bit. And I'm going to pull out the 2/3. And I'm going to distribute the x. And multiplying that in, we are going to get, now notice when I multiply here, the 300 is going to become 100 times 2 is going to be the 200x minus, and this is going to become 8/3 x squared. So there is my area function. And of course, to optimize that, I'm going to need to take the derivative. Let's do that over here, dA over dx. That's going to become 200 minus, and that's going to become 16/3 x. And to optimize that, we're going to set that whole thing equal to 0. And then we're going to solve for x. And I'm going to notice I'm going to divide or multiply it by the reciprocal, either way that you want to do it. That's going to become 600 divided by 16, which is going to be 37.5, and this is going to be feet. So there is one of the dimensions. Now to find the other one, I'm going to have to plug it into here. Let's see what we get. 300 minus 4 times 37.5 divided by 3. I'm getting 50. So the dimensions for the largest area are going to be 37.5 feet by 50 feet. That will give us the largest possible area for this configuration. All right, now we're going to get a little abstract, which is fine. We have a geometry student who wants to draw a rectangle inscribed in an ellipse. X squared plus 4y squared equals 9. We'll get to that. What is the area of largest possible rectangle that the student can draw? Okay, let's break down this ellipse a little bit. Now, if you remember an ellipse in proper form, it should be centered at the origin. Like this. And it's not in that form. You'll notice it's not equal to 1. So I'm going to divide through by 9. You divide through by 9. I'm going to get x squared over 9 plus 4y squared over 9 equals 1. Now, it's still not in this form. Well, what I'm going to do is a little algebra trick. And I'm going to bring that 4 down to the denominator. But to do that, it's going to make it look a little weird. This is plus y squared over it. This is going to become 9 over 4. Now, what this means is that A for us is 3. B for us is 3/2 or 1.5. That's going to matter when we draw our ellipse, just to get an idea of what it is that we're even looking at. That means in the x direction, I'm going to go a distance of 3. So this is going to be -3. This is going to be 3. And here, I'm going to go a distance of 1.5. So our ellipse is going to look like this. You'll pardon my bad drawing. I'll do the best I can with this. So there's our ellipse. And what we're trying to do is inscribe a rectangle. Inscribe a rectangle inside of this. And there's lots of rectangles that can be drawn. We can have a little tiny one over here. We can have a really broad one like this. What we're trying to do is optimize the rectangle of the largest area. Once again, we're trying to maximize the area of a rectangle. Now, the way that we're going to do this is we're going to call this point on the ellipse xy. And I want to point out that for this rectangle, the distance from here to here is x, which means the distance from here to here is also x. That also means that this is y, and that's also y. All right. Now, what we're going to have to do is rewrite y in terms of x. There we have it. And I'd like to point out that the area is actually going to be 2x times 2y. So we need to be extra careful here because we know that y is here. So this is going to become 4x times y, which is the square root of 9 minus x squared over 2, which reduces to 2x times the square root of 9 minus x squared. So there is our area function in terms of x only. I'm going to rewrite it. So now to optimize that area, we need to take the first derivative. Now I'm going to have to do product rule here. So derivative of 2x is just 2 plus 2x times the derivative of this. This is going to be 1 over 2 times the square root of 9 minus x squared times negative 2x. Now, again, if we view this like this is 9 minus x squared to the 1/2, remember that 1/2 comes down, that's where the 2 comes from. I do 1/2 minus 1, which is negative 1/2, which means it comes down to the denominator and becomes a positive 1/2, which I translated into a radical. So let's clean this up a little. You'll notice one of those 2's reduces out. And we are left with minus 2x squared, x times x, over the square root of 9 minus x squared. And we are now going to have to set that whole thing equal to 0. So what I'm going to do is multiply through by the LCD, which is the square root of 9 minus x squared. And root 9 minus x squared times root 9 minus x squared, the radicals cancel. So I'm left with 2 times 9 minus x squared. Actually, only one of these is negative, so we just have a minus there. Minus 2x squared equals 0, because that times 0 is 0. Okay, so now I need to solve for x. So that's going to be negative 4x squared equals negative 18, which means x squared is going to equal, when I divide by the negatives go away. I'm going to end up with a 9/2. Which means x is the square root of 9/2. Now, this time they're not looking for the dimensions. They are looking for, let's go back, they want to know what the actual area of the largest rectangle is going to be. So if x is 9/2, and remember my area function is here, I now need to get y, which if you recall, y is here. Here. You know what, let's keep this a little bit more simple. Let's just plug in x there. That way we can get the largest area. So area is going to be, and we're here, 2 times the square root of 9/2 times the square root of 9 minus, here's x squared, 9/2. Right, or we could square this, just becomes 9/2. This becomes 2 times the square root of 9/2. 9 minus 9/2 is 9/2. And you'll notice that gets squared. So the radicals go away. We just end up with an area of 9. Now we don't have any units here, so we don't know if that's, square inches, square feet, square centimeters, meters, whatever. But unit squared. So you may need to go back through with that one. There's a lot going on there, especially with the setup and the drawing and the whole deal there. So just take your time with it. We are to the last problem. And we have more rectangles, which is good. All right. A graphic designer is asked to create a movie poster with a 50 square inch photo surrounded by a 4-inch border at the top and bottom and a 2-inch border on each side. What overall dimensions, so we're looking for dimensions again, for the poster should the designer choose to use the least amount of paper? So now we're looking to minimize the area. All right, let's try to draw a picture here. So here's the overall poster. This is going to include the border. So I'm going to go here. Here and here. And in this direction, I'm going to go here. And that hopefully is going to give us 4 inches here. And 2 inches here and here. All right, I'm going to call the actual picture, I'm going to call that dimension, I'm going to call this X, and I'm going to call this Y. So I know that X times Y has to equal 50 square inches, which means that Y is 50 divided by X. Now that's just this inner poster here, inner picture, I should say. The overall poster, the area, is going to be different. This is going to be X plus 2 plus 2. So this is going to be X plus 4 times Y plus, that's going to be 4 plus 4. That's going to be 8. And rewriting that, I'm going to get X plus 4 times Y, which we know is 50 over X, plus 8. So here is our function of X for the area. I'm going to FOIL that together. X times 50 over X, the X is reduced out, I just get 50. The outer, X times 8 is 8X. The inner is going to give me 200 over X. And the last is going to be 32. I'm going to clean that up a little. So all I did was the 50 plus the 32 is the 82. All right. So to optimize this, we are going to have to take the derivative. This can be minus 200 over X squared. And we're going to have to set that equal to 0. Remember, derivative of a constant is 0, so that 82 goes away. We'll multiply through by x squared. Add the 200, divide by 8. That is going to give us 25. Again, 200 divided by 8, 25, which means x equals 5. Now, they want the overall dimension. So that's just the picture part of it, not the whole thing. So actually, x plus 4, 2 plus 2 plus x, is going to give us 5 plus 4, or 9 inches. So here's one of our dimensions, 9 inches. In the y direction, it's going to be y plus 4 or y plus 8. We know that y is 50 over x. X being 5. That's 10 plus 8. That's going to give us 18 inches. And there is our other dimension. Now, I know these are a little overwhelming, and you may need to go back through these and practice them a couple of times, but after a little while, it starts making a little bit of sense. I hope that helped.